Last time we left off with, we had just talked about the different types of lateral force resisting systems, right? So can anyone remember what those three types are?
Braced frame.
Yep, braced frame, very good.
Shear wall.
Shear wall, yes.
Moment
Moment resisting frame, excellent. So almost every single semester that I've taught this class, that has been a question on the first exam. What are the three types of lateral force resisting systems? Right, we got braced frame, shear wall, moment resisting frames. So just as a quick recap, right, we had going through here. Shear walls have the solid panel, right? Braced frames, you can have one or two diagonals there. Different configurations for a braced frame. Shear walls have solid panels. They can be made of any material that can resist shear, right? In high rises, sometimes you need to include outriggers with that shear wall. That doesn't make it a different lateral system from those three types. It's still a type of shear wall system, all right? But that just makes it possible for a high-rise structure. And then for moment-resisting frames, there are a few different configurations that you can have, but usually they involve this type of rigid joint. And we'll talk more about that stuff later on. We looked at pinned joint behavior as well, all right? So that's another important concept is what is the difference between a rigid joint and a pinned joint? How do they behave differently? What are the different assumptions associated with those joint connections? All right, so remember with a rigid joint, you maintain a 90-degree angle between beams and columns. So when that joint rotates, every beam and every column that frames into it has to rotate by the same amount and in the same direction. If you have a pinned joint, then the beam can rotate separately from the column, or that you don't have to maintain that 90-degree angle, right? All right, and then we looked at some examples. So this is where we left off. I added the pictures of these two men because they both have done a lot. They've had a huge impact on architecture and structural engineering in our modern society. So over here you have, of course, the World Trade Center Twin Towers. And both of these structures, by the way, are examples of high-rise moment-resisting frames. And they're different applications of that system in high-rise structures. So the World Trade Center towers consist of very closely spaced beams and columns, really. The spandrel beams are pretty deep. The columns are very closely spaced together, just about 2 feet apart roughly. And the reason for that is because the architect, Minoru Yamasaki, who is an American of Japanese descent, he was actually afraid of heights. And so he wanted to be able to feel comfortable, or he wanted anyone to be able to feel comfortable standing at the perimeter of the building towards the top, looking down out the window. And in order to do that, that's why the columns were so closely spaced together. And that happens to also be one of the reasons that the buildings were able to stand for as long as they did after they were impacted by those airplanes. Because that made for a pretty redundant outside system, right? So this is a tube system that consisted of interior column and core around the elevator shaft, and then all those perimeter columns, they resist that lateral load through moment frame behavior, which is a lot of shear and flexure. On the other side, you have the Sears Tower. I always fail to call it the Willis Tower, but that's the official name now. But Willis Tower, also known as Sears Tower. This was a system, right? So this is the first of its kind, a bundled tube system. So you can see how it truncates at different locations. So at the base, you have a bundle of 9 different tubes of equal size, and then it tapers down to just 2 tubes of that at the very top, right? And the engineer who developed that system is this guy right here, Fazlur Khan. He's a Bangladeshi American. He became a citizen in the 60s. And he is also behind the John Hancock Tower, which was the braced frame high-rise that we looked at earlier, and the Bank of China, which was that trust system, that space trust that I mentioned last time. So he developed this way of really achieving these great heights with the bundled tube approach, because that makes for a more efficient use of that moment frame behavior. Because one of the issues with moment frames is that as you know, they have significant deflections associated with them, so much more so than brace frames. So as a lateral load is applied, they're going to deflect quite a bit, especially the taller you get, that increases significantly. And so that essentially leads to what we call shear lag. And that's something that we'd like to try and minimize or avoid. And having the bundled approach really achieves that pretty well. On the other hand, right, the World Trade Center towers didn't use the bundled tube approach, but because those columns are so closely spaced together, again, it's a very redundant system, so it was effective in achieving the height of that tower as well. So that leads me to this comparison then between brace frames and moment frames. So you can see the image here demonstrating the difference in lateral deflections. And so what this leads to, as far as our analysis goes, is an understanding that in a brace frame, you have significant axial forces, right? Especially in that diagonal member. It primarily resists that lateral load through axial force. So there's very little shear and flexure in this response. Over here, however, all of your response, because there's no diagonal to take that, all of your resistance to the applied lateral load has to be done through flexure and shear. And so that's what you see in the bending. All right, now this is one example, assuming that these joints are rigid, which it looks like that's the intent because you can see the 90-degree angle. And then fixed supports at the base, you can see that flexure in the column. And technically there would be some flexure in the beam as well. In this image, because it's shown as straight, that's an indicator that this is representing a frame where the beam is much stiffer than the column. So in that case, the columns will flex more easily, and the beam will just have very minimal deformation there. But if the opposite were true, right, if the beam was similar to the column in stiffness or less stiff than the columns, then you would definitely see flexure in those beams as well. All right, questions so far? All right, so now to wrap up this set of lecture notes, before we roll into the gravity load path discussion, we'll look at some potential structural failures. So first of all, we have component failures, all right? So different types of material failures are shown on the left of the screen. A beam in bending, as you know, right? In positive bending, the bottom fibers will be in tension and the top fibers will be in compression. So flexural failure often occurs in the forms of tension cracks at the bottom if it's a reinforced concrete beam, for example. Other materials can also crack apart, of course, but we often see it in reinforced concrete. And you can have vertical shear failure, right? So that tends to occur towards the supports because that's where your shear force is going to be maximum. Whereas in flexure, your bending moment tends to be greatest at the center of the beam, if it's configured like this at least. And so that's where you'll expect to see that failure. Horizontal shear failure occurs, this is mainly a concern for components or beams that are assembled in layers. For example, glue laminated wood beams are often, constructed in layers, and so if that bond between the layers, the glue, isn't strong enough to resist the horizontal shear in that beam, then it will fail and those layers can just slip and slide right past each other. So we want to avoid that, of course. Bearing stress failure, that occurs at any location where you might have a concentrated force applied in compression. And so that could be a load or a support condition where the material would crush under that force. And then we also have torsion failure, which of course is due to twisting, and that's a type of shear failure, right? So all of these different material failures are things that we would need to consider on an individual basis. So generally speaking, these two are always considered for beam design, right? This one is not always something that you need to calculate. It depends on the beam and the situation. But it's definitely something that you want to make sure isn't going to happen. And then these guys are usually checks that we make on an individual basis after the actual beam is sized. So it doesn't really have much to do with the depth of the beam or the capacity of the beam. You might need to modify a few things at those locations. It's a localized check, right? So you might have to make a few adjustments at those locations, but you wouldn't want to upsize the whole beam for something like that, generally speaking. All right, so then on the right side we have geometric failure, different types. So first you've got column buckling, right? So that's a concern anytime you have a column in compression, especially if it's a slender column. And you have lateral torsional buckling, which is an issue with beams that span long lengths, in particular if it's a cantilever beam as shown here. So that, as it's shown, it represents kind of a twisting and bending out of plane. In order to avoid those failures, a simple fix is to provide lateral bracing at midpoints or endpoints wherever it's crucial, all right? All right, so then we have global structural failures and the corresponding, or one possible corresponding prevention shown below it. All right, so left to right, you've got overturning. We've talked about that a little bit in the context of high rises. All right, so here, the proposed prevention is a heavier foundation, and that may be appropriate in certain situations, but for a high-rise structure, you've already got a really heavy foundation, or you've got a deep foundation, so that may not be a practical solution. So that's where those outriggers come into play, right, to help prevent overturning. For sliding, the proposed fix is to provide tie downs or piles. These would be like friction piles in the foundation. And then lateral racking, this is what I was referring to earlier with moment frames, where you have shear lag due to that lateral deflection. Lateral racking is another term we use for it. Here the proposed fix is cross bracing, which is what's shown, but of course if you want a moment resisting frame, then you add cross bracing, then you have a brace frame, so that would defeat the purpose. Or rigid joints, right? And even with rigid joints, you'll still have some racking there. So that's just something to keep in mind. But the more you stiffen up those joints, the less that racking will occur. And then lastly, you have all those different types of member failures that we talked about on the previous slide. And the solution to that is to really make sure that your members are sized appropriately. All right, questions? Okay. Yes?
If you have a lot of lateral racking, why wouldn't you just make it across, right?
A braced frame?
Or a braced frame, yeah.
So a lot of times that comes down to what the architect and the client want aesthetically, honestly, yeah. Yeah, that's pretty much what it comes down to. Because if they want a certain look, then braced frames don't fit it, then it's, yeah. So, and we can make moment frames work, right? We can deal with it. We have ways to do that. But it is just a different expectation that we have for the building. So, yeah, good question. Any others? All right, so now, just kind of a fun, just for fun, what type of wall do we see over here?
Shears.
Yeah, shear wall. All right, so this is a reinforced concrete shear wall. What about this?
Is it an aesthetic wall?
Yep, it's an aesthetic wall, right? Translucent, so light can shine through it. A different type of shear wall, okay? And I like to put this up here because notoriously engineers are terrible at spelling, right? So I cannot tell you how many times I've seen a shear wall referred to as a shear wall, which it better not be, right? Because if it's actually shear, S-H-E-E-R, then it's not going to be an effective S-H-E-R, S-H-E-A-R wall, okay? So yeah, so that's just for fun. But this is actually a pretty cool product. It's called light transmitting concrete. It is purely non-structural, right? So it's just for good looks or interesting architecture. And yeah, it can be used in non-structural purposes. So, all right. So now I'm going to jump over to the gravity load path discussion. So we just talked about lateral systems and lateral loads. Now we're going to talk about gravity loads. So we looked at this last time, right? This is the example of a vertical load path where you've got the floor surface is the first line of defense, and then that transfers forces to beams, for example. Could also just be a flat plate. You don't necessarily need a whole network of beams. You might just need beams on the perimeter. It depends on the system. And then whatever you have at that level would transfer those forces to the vertical elements, being the columns and or walls, and then those would transfer to the foundation. So the floor system, when we say that, we're referring to whatever structural flat plate we may have, and then any beams that are in play. And that also includes knowing where the support points are. So the support points would, of course, be columns and walls, or maybe other beams, depending on what we're looking at. Now, looking at those vertical elements, this note pointing out that if there are walls present in the gravity system and they're participating in that system, they can replace some beams and reduce the number of columns that are needed. So again, it just kind of depends on how you want to use them, or if you want them at all. All right, so now we're going to look at a couple different types of floor systems and go through some vocab. These floor systems are also included in the skeleton notes handout that's designated for Friday. So we may touch on that a little bit today, but I'm not going to do much, if any, writing that goes on that. So, but FYI, they are repeated on that set of lecture notes for your reference. So you can draw more on them if you want. All right, so first we have an example of a one-way floor slab or system. All right, and here you've got a bunch of beams, and we definitely need some beams or walls in order to make sure that the load path is complete, because in a one-way floor slab, the floor surface is only capable or only designed to transfer load in one direction. All right, so that would be, in this example, in this direction here. So these beams would be directly supporting that surface. They would be taking those loads, and then those beams would transfer those forces to these girders, which would then transfer to the perimeter girders and so on. If we have a two-way floor slab or span, then you may or may not need beams or walls to support that slab, right? They can just be supported by columns, because that slab is capable of transferring forces in two orthogonal directions. So a little bit of things pointed out there, right? You've got different columns shown, cross beams, and girders. So we're going to go into the definition then of different beam terms. So girders are specifically beams that support other beams, right? So you can see them shown. We've got the same floor plan with different terminology highlighted. A primary beam is a beam that stands between columns, right? So the definition of girder is tied to what the girder supports. The definition of primary is tied to how that beam is supported. So it can get a little bit confusing, but we kind of use all of these terms sometimes individually, sometimes together. And then cross beams would be beams that are, they could be supported by columns or girders, right? But they're generally referring to beams that directly support the floor surface or slab. And then secondary beams are specifically beams that are supported by primary beams, right? So supported by other beams. So in a different floor layout, we can see how this girder would be also considered a secondary beam. This girder would be considered a primary beam, because here you've got these beams are supported by columns, but this is a beam that is supporting other beams, right? So we might call this a primary girder and this a secondary girder. And then you've got the cross beams and secondary beams shown there. All right, primary girder, secondary girder. All right, questions about that? There is a glossary on D2L under course resources, I believe, that should have those terms in them in case you want to go back and refer to it. All right, so now we're going to introduce the concept of tributary area. Here's the note on the glossary items. So you can find this definition there as well. It says basically you have to consider the element that you want to know the tributary area for. All right, so every individual component has a tributary area. Column has a tributary area. Every beam has its own tributary area. And it's defined as it's defined by boundaries that are drawn halfway from the element that you're considering to the next supporting element of the same type or at the same level within the load path. Did I say halfway to? Yeah, halfway to the next one in any given direction. So most times it's pretty straightforward. Sometimes it can get a little bit tricky. But here, if you have a pretty regular layout like this, right, here's an example of column tributary areas. So the interior columns tend to have the greatest tributary area. Corner columns tend to have the smallest tributary area. If you have a shape, something like this, you can see the different tributary areas of those columns, which are noted by the squares or circles at the perimeter. They just get shaped differently, right? So you might need to use a CAD program to calculate what those are versus doing it by hand. And then if you have an irregular column layout like this, the tributary areas can get pretty complicated. So that's not always avoidable. Sometimes you're going to have irregular layouts and awkward tributary areas to calculate, but in general, right, it shouldn't be too out of hand. So here you can see different tributary areas highlighted for columns in this floor layout. But this is pretty extreme, I would say. So that is something that I would definitely want to avoid as a structural engineer. Looking at this, and this is all reinforced concrete, all right? So look at all that stuff that's going on there. I can't even imagine the headache that it was to construct the formwork and figure all that out. So, I hope that if any of you end up designing structures, I hope nobody does anything like this. So. All right, now here's an image showing the tributary areas of different beams. Again, halfway to the next supporting beam of the same level, all right? So for this one, which is a cross beam that directly supports the floor plate, we would go halfway to the next beam that directly supports the floor plate on either side, right? But for this one, which is a girder, we would go half the distance to the next girder that supports it on the same level. So this is showing the areas, but with beams, we're generally more interested in the tributary width. And that is specifically the dimension of the tributary area that is perpendicular to the length of the beam. All right, questions so far?
That's all from a bird's eye view, right?
Yeah, these are all plan views that we're looking at, yep. Any other questions? Okay. So what do we use these for? Well, a number of different things. Initially though, we're just going to be concerned with using tributary areas and width for the purpose of calculating loads through the load path. So tributary area would be used to condense a surface load in pounds per square foot to a point load. For example, if we want to know how much that a specific column is supporting, right? What is the point load on that column from the surface load on the floor? We would use tributary area to calculate that. And then similarly, we would use tributary width to condense a surface load to a line load on a beam, for example. So we would take that PSF load times the width, that one dimension of the tributary area of the beam, to get a line load in pounds per foot. Or we would condense a line load on a beam to a point load, maybe where it frames into a girder, right? So if we're looking at a girder, we want to know what the point loads are at the locations where the cross beams frame into them. We would use the tributary width of those cross beams to calculate that load. And this is something that you're going to get to practice with homework 2, which I should have available to you by the end of the day today, I think. So with that, let's see. So that didn't take nearly as long as I thought it would. All right, so any questions? Here at 9:30. All right, how about homework 1? Any questions on homework 1? Due Friday, right? Got matrix algebra, drawing deflected shapes. Everybody have the book? Copy, hard copy or electronic? How many folks got the hard copy? I'm just curious. A handful, all right. Most people got electronic version, all right. All right, so I trust everything is going well with that. So I guess what I'll do now, and I'm not gonna get into the let's see. Here we go. All right, so here's the set of skeleton notes that is designated for Friday, and we will be diving into this on Friday for sure. But there are a few pages that I can just talk about without doing a whole lot of writing, and I don't want to leave anyone in a bind in case you weren't prepared for it since it was designated for Friday. So here again is that page where we have the one-way span floor layouts shown, or there's two different ones shown here, and then the two-way span is on the next page. So we can look at this, all right, and you can imagine what the tributary areas are. All right, so if we have this girder here, the tributary area of that girder would just be essentially half of the floor slab, right? Because we would take half that distance to the next girder. These girders would be considered to be on the level above that within the floor plane, right? The floor layout. So each of these girders would have tributary areas outlined by lines roughly around here, right? Halfway between those those four beams. And then each column in this floor layout would support a quarter of the floor. So that that one's pretty straightforward as far as the columns go. Over here, we have a slightly different scenario, right? So we don't have any secondary girders, right? All of our girders are primary beams because they're all supported by columns. And so each of those girders would have tributary areas defined by lines just halfway to the next adjacent girder. And then similar for the cross beams, right? Your tributary areas would look like that for the cross beams. And it's normal for tributary areas to overlap among elements that are not in the same level of the load path, right? So the level of the load path would essentially be the floor to the cross beam to the girder to the column, right? So the cross beams would all be on one level, the girders would all be on the next level, and then the columns would all be on the last level. And then for the two-way span, of course, right, we just have that slab transferring load in both orthogonal directions. You probably would have some kind of beam at the perimeter there. And then down here we have definition of span. So in a structural engineering context, span could mean two different things, all right? It can be used to communicate a distance, all right? The distance between supports for a given structural element. And this is typically, the distance is typically either vertical or horizontal, depending on what that element is, right? So beams typically have horizontal spans, columns typically have vertical spans. An exception here is noted down below, I think, right? So yeah, so an exception to this is a rafter that would be part of a sloped roof. In that case, the span is still horizontal, it's not along the length of the member. All right, so yeah, so the exception is speaking to the second part of the sentence before that, right? In both cases, the span direction is parallel to the length of the element, with the exception of that sloped rafter. The other use of the word span is shown here, right? So that can be used to communicate the direction of the load path within an element, right? So you'll hear me say that a lot in this class, referring to span in both contexts. All right, questions so far? Okay. So then on the next page, we've got a few examples of actual one-way, two-way slabs. So up at the top, whenever you see corrugated metal decking, that's always a one-way floor system, right? So it may or may not have concrete on top. In this example, it does. So you can see the reinforced concrete there. And it's reinforced in two directions, but the span is still going to be in the direction of the metal decking, parallel to the flutes, right? And so this is, let me see if I have this paired. Yeah. All right, so this is similar to, right, taking a piece of paper and folding it like that. In this direction, it's really floppy, right? But in the other direction, it's pretty strong. I've done this before. Let's see if I can do it again. I've even used it to support my cell phone in this direction, right? So pretty strong in this direction, but if I try to do that in this direction, which will be a little tricky for me, because, yeah, right, that's not going to work, right? So, and thank you. Appreciate that. So you can intuitively understand why it's just a one-way span. So you can always tell, looking below, right, what direction that floor is spanning, right, because you see the direction of the metal deck. So then you can identify, okay, this is a cross beam, this is a girder, right? And usually it's also easy to tell because girders tend to be a lot deeper than cross beams. Not always, sometimes they're similar in depth, but often that's the case. And then with two-way slabs, here's a couple different types of two-way slabs you might see. This one is not really used anymore for new construction, but you might see it in older buildings. It's called a waffle slab, and the formwork is essentially looks like a waffle iron, and so the concrete is poured, and you've got a network of these grids of beams essentially built underneath and integrated into the slab. And so, that was a pretty popular way to construct these long span two-way concrete slabs. But since then, we've come up with more efficient ways to do it. So over here, you see a flat slab with what we call drop panels. So I'll just note that on here. All right, so that's a drop panel. And that is purposely to thicken the slab at the locations where the columns will support it to avoid that column punching through the slab, which we call punching shear failure. So we want to avoid that at all costs. Or you could have just a flat slab without those drop panels, right? And so that might require a thicker slab overall. In this scenario with the drop panel, you can achieve a thinner slab in most of the area, all right, and just thicken it at the locations of the columns. All right, so now we've got some one-way roofs shown here. All right, so these are, the first two are just showing the joists that would support the roof. The roof, of course, is not yet in place, the roof surface anyway. But just by looking at where the joists are placed, you can tell how the surface will span, all right? So it'll span perpendicular to the length of those joists. And in this scenario, these joists are supported by masonry, bearing walls, and shear walls, all right? So you can see, it might be a little hard to tell in the image, but those are masonry walls, not concrete walls. And then down here, right, you have a similar scenario. These are composite joists, wood and probably aluminum, maybe steel in there. And these are supported by metal stud walls. They'll most likely have OSB plywood sheathing that would serve as shear walls for that system. Or they could have maybe gypsum in there, so that's another common application. But that's what I would predict for that system. And then, of course, here the roof surface is in place, so you can see the direction of those spans. All right, questions? No questions? Okay. Well, I'm going to stop here with the lecture notes because then we'll just dive into some writing calculations and examples on Friday. But since we do have a little bit of extra time, I just want to check again. Anybody have questions on the homework? How are you liking drawing deflected shapes?
I haven't started yet.
Okay, all right. I appreciate the honesty. Well, my hope is that you'll start to develop an appreciation and maybe even an enjoyment of drawing deflected shapes of structures, because it's something that I'm going to ask you to do, and it's not going to be necessarily part of every single problem that you're assigned, all right? But I'm going to challenge you before you dive into analysis of any structure in this class. Just imagine how it would respond, all right? Try to imagine that deflected shape, and draw it if you want to. Unless you're specifically asked to draw it in the homework assignment, it won't be required. But that's a really good way to start developing your intuition, thinking about how that structure will behave and respond, taking the supports into consideration. It's really going to strengthen your understanding of structural behavior. So that's why I build it into the very first homework assignment, and then I try to encourage you to continue that practice on your own. All right, good deal. Well, we will keep you posted on office hours for Mohammed, your TA for this class. So probably for this first assignment, it's not as essential. It's pretty straightforward stuff, but by next week, we hope to have that sorted out for you. Okay, so keep an eye on D12 for announcements. And with that, I will let you go. This is very rare, by the way. Letting class out early almost never happens with me. So, so appreciate it while you get it.
Oh, are these the three